Hello everyone. Today I will present my assignment 6, design and simulation of third order transfer function based on system uh, identification. Uh, the core objective of this project is to establish a third order transfer function model for an unknown rotating system through system identification methods and simulation in Simulink to verify the accuracy of the model. Firstly, I will choose a suitable physical model as the research object. Next, I will use MATLAB to simulate and generate the input and the output data of this system. Then, using MATLAB's powerful system identification toolbox, study the uh, mathematical um, math mathematical model of the system from this data. Finally, I will simulate the ID, identified model together with the original model in Simulink and evaluate the success of the identification work by comparing their outputs. For the system model, I choose a very classical example, the dual mass rotation system. It consists of a motor, a flexible shaft, and a long flywheel. The motor provides power and drives the low slope flexible shell with electricity. This flexible connection is crucial as it introduces additional dynamic behavior, increasing the order of the entire system from simple second order to third order, perfectly meeting the requirement of our assignment. Next, let me briefly introduce the core story of this project. System identification. System identification is a black box modeling method. Here we need to know the exact physical equation inside the system. We only need to observe its response to specific inputs, such as a step signal to infer its estimation model. Our goal is to find a third order transfer function of the from this tab and uh, determine is for unknown parameters. Now we are entering the pressure phase. Firstly, we need a real system to provide data. I define a third order transfer function in MATLAB as our research object. Then I apply a unit step input to it and simulate its output. In order to make the data more realistic, I add a 5% Gaussian white noise to simulate measurement errors. This image clearly shows the clear, slow read so output, blue light, and the noise data that we can actually measure engine does. Our identification work will be entirely based on this orange data. While the data we can proceed with the system and identification. In MATLAB, I first package the input and the output data into an iData object. Then using the fast function and specifying a modern order of 3, MATLAB will automatically calculate the most matching third order transfer function for us. As you can see, the identity model G has been displayed here. This is the system model we obtain atomic slow data reverse engineering. So is the identity model calculate. We need to verify it. I use the step input to drive the identity model. G is the and compares the response with the initial true system response from this graph. It can be seen that the two curves in blue and the red almost compelling overlap. This indicates that our system identification was very successful, and the obtained model can simulate the dynamic characteristic of the original system very well. Now, we entering the Simulink simulation phase. I have built a very intuitive model. On the left is a stable input signal that is simultaneously input in parallel to transfer function modulus. The top one is our true system, and the bottom one is the system we have identified. Finally, the two outputs are matching through a max model and sent to an oscilloscope for observation and comparison. In Simulink, the key is to correctly set the parameters of the transfer function model. We can directly copy the numerator and the denominator coefficient of G is from the MATLAB workspace, making sure add a 0 before the numerator. Meanwhile, in order to obtain small and accurate simulation result, I set the solver to order 45, which is the which is a very versatilely variable step of slow table for such dynamic systems. After running the simulation, we can see final result on the oscilloscope. The yellow curve represents the response of a real system, while the blue curve represents the representation of the identification model. As we have seen before in MATLAB, the two are almost identical. This call again strongly proves that a model we obtain through systems identification is array and reliable and can properly reproduce the behavior of a real system of the true system in Simulink environments. To sum up, this project successfully system identification muscles to establish a mathematical model for a third order rotating system, and its accurate was verified through Simulink simulation. We have demonstrated the complex engineering process from data generation, model identification to simulation verification. This project not only deepened my understanding of transfer function and the system dynamic, but also enable me to master the powerful application of MATLAB and Simulink in control system analysis and design. And thank you for watching my video.